Over the next 7 weeks, you will work as part of an interdisciplinary, NASA-inspired contract team moving through the full life cycle of a mission concept, not simply imagining an idea, but developing it into something structured, testable, and presentation-ready. Throughout the term, you will participate in a sequence of faculty-led workshops that support the major dimensions of the project, including business proposal strategy, structure, and writing, the application of mathematics in planetary robotics, biological considerations in planetary exploration and colonization, engineering design and prototype development, and the physics of forces, power, and planetary conditions. Alongside these workshops, your team will select a mission pathway, define its objective, and design, build, and test a prototype rover using the robotics kit and related components within a simulated Mars mission challenge. You will progress from early concept development and systems thinking into rover mission planning, sensors and data systems, mobility and drive systems, programming and controls, assembly, testing, refinement, and final reporting. At the conclusion of the experience, each team will submit a formal NASA-style business proposal, demonstrate its rover in the competition environment, and deliver a final presentation explaining the mission, the design, the logic behind the system, and why the team's concept deserves to win. With that larger picture in mind, today's workshop focuses on the foundation for everything that follows: the opportunity itself, the mission mindset, and how to begin building a serious proposal from the very start. To be clear, what you are stepping into here is not just a robotics project, and it is not just a proposal writing exercise. You are stepping into a miniature version of how real missions begin. NASA does not start with a machine. NASA starts with a problem worth solving, a question worth answering, a risk worth taking, and a team capable of turning uncertainty into disciplined action. That is the spirit of this experience, and that is why this project matters. NASA's NCAS program exists to engage community college students in authentic NASA learning experiences and help build a diverse future STEM workforce. It is meant to move students from interest to capability, from curiosity to contribution, and from classroom learning to mission thinking. NASA Jet Propulsion Laboratory, JPL. So as you listen to this, I want you to frame the entire project differently. Do not think, we are building a robot for class. Think, we are forming a mission team. Do not think, we are writing a document because a professor asked us to. Think, we are making the case that our idea deserves resources, trust, and support. In your competition, that case is not secondary. The business proposal is worth half of the total score, which means it carries more weight than any other single component. The proposal is where you show mission logic, design purpose, planning discipline, NASA alignment, and team readiness. Now let us begin with the larger picture. Why Mars? Why does NASA care so much about this planet? Mars matters because it sits at the center of several of the biggest questions human beings can ask. NASA's Mars exploration goals are to determine whether Mars ever supported life, understand the history and processes of its climate, understand its geology and evolution, and prepare for human exploration. Mars is also described by NASA as a horizon goal for human exploration, because what we learn there may help us understand whether life ever existed beyond Earth, and may also teach us something important about Earth's own past and future. NASA science. That means Mars is not just interesting because it is far away. Mars is scientifically important, operationally difficult, and strategically relevant. It is scientifically important because it may preserve clues about habitability and past microbial life. It is operationally difficult because of terrain, dust, radiation, temperature swings, communication delays, and power limitations. It is strategically relevant because every robotic mission to Mars helps prepare for more advanced robotic systems and eventually for human missions farther from Earth. NASA's Moon to Mars strategy, including Artemis and the larger architecture around it, is explicitly about building the systems, knowledge, and operational experience needed for long-term exploration beyond Earth orbit. NASA. So when you work on this project, you are not pretending to solve a fake problem. You are practicing inside a real category of problems NASA is actively trying to solve. The question is not whether robotic systems matter on Mars. They already do. NASA has landed rovers and landers there, and missions like Spirit, Opportunity, Curiosity, and Perseverance have completely changed our understanding of the planet. The real question is, what comes next? How do missions become more autonomous, more focused, more efficient, more adaptable, more affordable, and more useful for future science and human exploration? That is where your opportunity begins. NASA science. And that word matters. Opportunity. A great deal of this workshop is about learning how to see opportunity properly. Most people see Mars and think only about distance or danger. Scientists see unanswered questions. Engineers see system constraints. Mission planners see requirements and trade-offs. Entrepreneurs see unmet needs. Real opportunity recognition begins when you learn to identify the gap between what exists and what is needed. If current rovers are powerful but expensive, there may be opportunity in lower-cost modular systems. If current missions gather great science but move slowly, there may be opportunity in better terrain intelligence or coordinated small unit exploration. If future human missions will require environmental reconnaissance, sample scouting, cargo support, hazard detection, or inspection tasks, then there is opportunity in mission-specific robotic systems built around those needs. NASA science. That is why this project should be approached through both a scientific and an entrepreneurial lens. Scientific thinking asks, what do we need to know, and how can we test it? Entrepreneurial thinking asks, what problem deserves solving, what value would the solution create, and why are we the team to pursue it? The strongest teams will combine both. They will not just build something that moves. They will define a mission problem, explain the value of solving it, connect their design to that problem, and show why their solution is realistic enough to be taken seriously. This is where many teams either rise or fall. Weak teams begin with the object. They say, let's build a rover. Strong teams begin with the mission. They say, there is a specific challenge on Mars that needs to be addressed, and this rover exists to address it. That is a profound difference. The first mindset produces gadgets. The second produces proposals with direction, seriousness, and strategic power. Your competition already gives you mission pathways, and they are more meaningful than they may first appear. One pathway focuses on identifying and collecting biological signatures, using biosensors, sample extraction, and environmental data logging. Another focuses on habitat reconnaissance and terrain analysis, using navigation, environmental sensing, and obstacle avoidance to assess areas relevant to future human settlement. A third focuses on colonization support, with tasks such as cargo transport, inspection, and emergency response functions. These are not random themes. They map naturally onto real NASA interests, past life, planetary science, environmental understanding, and preparation for long-term human exploration. NASA science. Let us take those one at a time in practical terms. If your team chooses a biological survey-style mission, you are entering the logic of astrobiology. NASA's Perseverance science objectives include studying habitability, seeking signs of past microbial life, collecting and caching samples, and preparing for future human missions. So a strong biologically oriented rover concept would not simply say, our rover looks for life. That is too vague. A stronger concept would say something like, our rover is designed to gather environmental and soil-related indicators in locations where signs of past habitability are more likely to be preserved. That is better because it sounds like a mission asset, not a fantasy claim. A weak version would promise direct proof of life with no credible sensing method, no sampling logic, and no explanation of what data would actually be collected. A stronger version would talk about practical proxies, location selection, environmental readings, simple material collection, image capture, or sensor-triggered markers that imitate the logic of biosignature search. NASA science. If your team chooses habitat, reconnaissance, and terrain analysis, you are entering the logic of surface operations. Future human missions need knowledge before people arrive. They need to understand terrain stability, hazards, routes, environmental conditions, and where systems can safely operate. A strong rover in this category might emphasize mobility, mapping, navigation, obstacle detection, and environmental measurement. A weak version would simply say, "We built a rover that drives around and avoids objects." A stronger version would say, "We designed a reconnaissance rover that evaluates traversability, identifies hazards, and gathers environmental indicators relevant to surface planning." That sounds like something NASA might actually care about because it translates movement into mission value. NASA. If your team chooses colonization support, you are entering the logic of infrastructure and operations. Long-term presence on another world is not built on one heroic machine doing everything. It is built on support systems, cargo handling, inspection, route assistance, system checks, emergency response, modular attachments, repeated tasks, and operational reliability. A weak version of this mission would promise that one rover will build habitats, carry huge loads, inspect power systems, and perform rescue operations all at once. That sounds exciting, but it sounds unrealistic. A stronger version would choose one function clearly, such as small-scale payload transport, modular equipment delivery, or inspection support in simulated mission conditions. That is what mature teams do. They choose a clear operational function and design around it. This brings us to the heart of the proposal itself. A proposal is not just information. A proposal is judgment on paper. It shows whether you understand how to think clearly. Your competition guidelines call for sections such as executive summary, mission objective and rationale, technical design overview, systems engineering approach, risk assessment and contingency planning, timeline and project management, budget and resource allocation, testing and validation, NASA mission alignment, team qualifications and roles, sustainability and future use, and optional appendices. Each one of those sections exists for a reason. Together, they answer a single question. Why should this team be trusted with this mission? Start with the executive summary. This is not where you ease into the topic slowly. This is where you establish that you understand the problem, the solution, the value, and the ask. Think of it as the compressed version of your whole mission case. In under a page, a reader should know what challenge on Mars you are addressing, what your rover is intended to do, why that matters to NASA, what makes your team credible, and what resources or support the mission requires. The best executive summaries do not start with broad statements about space being important. They start with a gap. For example, future Mars operations require low-cost systems capable of conducting targeted reconnaissance in terrain that may be too risky or inefficient for larger vehicles. Our team proposes a compact, autonomous rover designed to assess traversability and gather environmental indicators that support mission planning. That works because it begins with need, not filler. Now consider what would not work. Mars is a planet of interest, and our team has always been interested in robotics. We decided to build a rover because NASA uses rovers. That is weak, because it says nothing precise about the problem, the mission function, or the value created. A summary like that sounds like students beginning an assignment. A strong executive summary sounds like a team stepping into a mission need. Then comes mission objective and rationale. If there is one area where student teams often hurt themselves, it is here. They try to sound ambitious by doing too much. They end up with objectives that are broad, messy, and impossible to test. A good mission objective is specific, aligned, and meaningful. It says exactly what the rover is supposed to accomplish and why that accomplishment matters. The rationale explains why that mission is worth attention now. A poor objective would be, our rover will help NASA explore Mars in multiple ways. That is too general. A stronger objective would be, our rover will detect and map surface obstacles and terrain hazards in order to support simulated route planning for future surface operations. That is specific. It suggests data, testing, and mission relevance. The rationale should connect to real NASA logic. NASA's current Mars science emphasizes life potential, climate history, geology, and future exploration. Artemis and the broader Moon to Mars effort emphasize the development of systems and operational knowledge that support longer-term human exploration. So your rationale should not say only that your idea is cool or innovative. It should say why your mission contributes to exploration goals NASA already cares about. NASA science. Then there is team alignment. Many students assume team quality is mostly about intelligence. It is not. Team quality is often about shared clarity. Can every member explain the mission in one sentence? Does everyone know what success looks like? Does each person know their role in the build, the proposal, and the presentation? If not, the final work will feel fragmented. The proposal may still be completed, but it will sound like separate pieces stitched together rather than one coherent mission argument. Teams with moderate talent but strong alignment regularly outperform teams with more technical ability but weaker coordination. A practical way to think about alignment is this. If someone stopped each teammate in the hallway and asked, "What problem is your team solving, and how is your rover solving it?" the answers should sound like they came from one team, not 4 separate clubs. That is what alignment feels like. Now let us move into technical design, because this is where imagination and engineering have to meet honestly. NASA does not fund pure fantasy, but it also does not reward boring, underdeveloped thinking. The sweet spot is bold, but feasible. Your design must be interesting enough to matter and grounded enough to believe. The core technical questions are straightforward. How does the rover move? How is it powered? What does it sense? What onboard computing does it use? How does it communicate? And what payload or mission-specific mechanism does it carry? Start with locomotion. On Mars, movement is not just movement. Terrain matters. Regolith matters. Slopes matter. Stability matters. A good design choice is always tied to mission needs. If you are doing habitat reconnaissance, your movement system should emphasize stable navigation and traversability. If you are doing support operations, you may care more about carrying a small payload reliably. If you are doing a biologically inspired or lower-cost concept, you may explore smaller units or modular designs. A weak design section simply lists parts: wheels, motors, frame. A strong design section explains why those choices suit the mission. For example, we chose a wider wheelbase and lower center of gravity to improve stability during simulated terrain traversal. That sounds thoughtful. Then power. In your competition environment, the power discussion is conceptual and prototype-based, but it still matters because it reveals whether you understand systems limits. Real Mars missions care intensely about power because everything depends on it. Perseverance uses a radioisotope power system in the real world, while smaller student prototypes may rely on batteries and simplified power planning. The point is not to copy NASA hardware exactly. The point is to show that you understand energy as a design constraint. A weak proposal ignores runtime, load, and power trade-offs. A stronger proposal says, our prototype uses battery power sufficient for repeated short-duration testing, and our conceptual mission logic accounts for energy conservation by limiting non-essential actions during operation. That is better because it thinks beyond the parts list. NASA science. Then sensing. What the rover senses should flow directly from the mission, A terrain rover may need obstacle detection, distance sensing, visual markers, environmental measures, or route awareness. A biological survey-style rover may focus on environmental conditions, imagery, target detection, or simple sample-related triggers. A support rover may need load state awareness, route confirmation, or equipment inspection signals. A weak proposal says, "We added sensors." A stronger proposal says what the sensors are for and what decisions or actions they enable. This is also where biology can become a real source of innovation. Bio-inspired design is not about throwing in an animal reference because it sounds impressive. It is about translating useful biological principles into engineering logic. Tardigrades suggest resilience. Gecko feet suggest adhesion concepts. Slime mold suggests path optimization. Swarm behavior suggests distributed sensing and task sharing. Extremophiles suggest thinking about survival in harsh conditions. If you choose to draw from biology, do it carefully. Explain the principle you are borrowing and the engineering form it takes. A weak version would say, "Our rover is inspired by a gecko." A stronger version would say, "We were inspired by biological strategies for traction and surface interaction, which led us to think about stability and grip under low traction conditions." That is much more mature. From there, the conversation becomes systems engineering. This is one of the most important mental upgrades you can make during this project. NASA does not fund disconnected parts. NASA funds systems. A rover is a system made of subsystems: mobility, power, computing, communication, and science payload. If one fails, the others can be affected. A team that thinks in systems will sound more advanced because it understands relationships, not just components. For example, imagine a team proposes excellent sensors but ignores processing limits. That is not a system. Or imagine a team designs a payload arm that is impressive on paper but destabilizes the rover during movement. That is also not a system. Or imagine a team adds many functions without considering battery drain. Again, not a system. Systems thinking means asking, how does this subsystem affect the others, and can the whole machine perform the mission reliably enough to matter? This is why requirements should come before building. Mission need should lead to requirements. Requirements should shape architecture. Architecture should guide design choices. Then you build, integrate, verify, and validate. If you build first and think later, you often end up with a machine that exists without a strong reason for existing. That is one of the biggest traps in student projects. Risk assessment is where professionalism begins to show. Real teams do not pretend everything will work perfectly. They identify what might go wrong and decide what to do about it. In your project, risk is not only technical, it can also be organizational. Technical risks might include loss of traction, component failure, unstable wiring, weak communication between modules, poor sensing accuracy, or limited battery life. Organizational risks might include unclear team roles, schedule slippage, insufficient testing time, or one student holding too much of the project knowledge. Your materials encourage use of a formal risk matrix with likelihood and impact scoring. That is excellent because it pushes you to think ahead instead of reacting late. A weak team says, "We will figure it out if something goes wrong." A stronger team says, "We identified wheel slippage on loose terrain as a medium to high risk, so we will test movement early, document performance, and revise the tread or weight distribution if needed." That is not just a technical statement, it is a trust-building statement. It tells judges that you are serious enough to anticipate failure points before they become mission-ending. Timeline and project management work the same way. Many students treat timelines as administrative filler, but they actually reveal maturity. A vague timeline says the team does not understand scope. A clear timeline says the team understands sequence, dependencies, and discipline. Research should come before design finalization. Design should come before full build. Testing should happen before final presentation. Revision should happen after testing. Documentation should happen throughout. Your workshop materials also introduce technology readiness levels, which is useful because it teaches a key lesson. Not every technology is equally mature, and maturity should be described honestly. Basic principles, lab proof of concept, component validation, and system demonstration are different stages. You do not have to pretend your prototype is flight-ready. You do have to show what stage you are in and what evidence supports that stage. Budget is another area where seriousness becomes visible. A budget is not just arithmetic, it is design logic in numbers. What materials do you actually need? What does each item do? Why is it worth its cost? What campus resources or in-kind support reduce cost? What is essential and what is optional? Your competition specifically scores budget and resource justification, so this section has to show efficiency and thoughtfulness. A weak budget might lump everything into vague categories such as supplies or miscellaneous. A stronger budget names controllers, chassis components, motors, sensors, wiring, fastening materials, testing materials, and contingency. Even if your actual prototype is modest, the way you explain the resource logic can demonstrate maturity. The point is not to inflate numbers. The point is to show stewardship. Real organizations trust teams that understand trade-offs and justify costs clearly. Then there is testing and validation, which may be the single best teacher in the whole project. A proposal without a testing plan is basically a wish. NASA cares about whether systems work, not just whether teams can describe them. Testing is where design meets reality. Can the rover move over simulated terrain? Can it avoid obstacles? Can it carry a target payload? Can it collect or identify what it claims to handle? Can it repeat the task? Can it do so consistently enough to be useful? And here is something important to understand. Testing is not about proving that you are perfect. Testing is about proving that you are real. A failed test is not automatically bad. If you document the failure, learn from it, adjust the design, and improve, that can actually strengthen your proposal because it shows engineering honesty. A team that says, "Our first run revealed instability during turning, so we reduced top speed and adjusted weight placement," often sounds more credible than a team that claims everything worked smoothly but offers no evidence. Now let us talk about team roles, because ideas rarely succeed through enthusiasm alone. They succeed through organized contribution. Strong teams usually have clear ownership. Someone owns systems integration. Someone owns build and fabrication. Someone owns code or control logic. Someone owns the scientific rationale or mission logic. Someone owns budget and proposal narrative. Someone manages timelines and communication. That does not mean roles cannot overlap, but it does mean responsibility should be visible. When no one owns a task, the task usually weakens. When one person owns everything, the team becomes fragile. NASA alignment is one of the most strategic sections in the whole proposal. It is not enough to say your work helps NASA. You need to show how it supports real NASA priorities. A biologically oriented mission can align with seeking signs of past microbial life and with habitability-related science. A terrain or habitat mission can align with understanding environments relevant to future surface operations. A support rover can align with the larger logic of sustained exploration and operational capability. Artemis is explicitly part of NASA's path to the Moon and then onward to Mars, and the broader architecture emphasizes integrated systems for living and working on the lunar and Martian surface with safe return to Earth. If your proposal maps clearly onto those ideas, it sounds relevant. If it mentions NASA only in general terms, it sounds superficial. NASA. Sustainability and future use push your thinking one step further. A mature team asks, what happens after the competition? Does the idea stop here, or could it be reused, scaled, adapted, or improved? Could next year's team inherit and advance this platform? Could the concept evolve into a stronger prototype, a campus research project, an outreach platform, or a future grant idea. The purpose of this section is not to exaggerate. It is to demonstrate that you see your work as part of a trajectory, not just a one-day event. At this point, it is worth zooming out and asking a bigger question. What is NASA really trying to achieve through students in a program like this? The answer is larger than one competition. NASA needs future scientists, engineers, technologists, analysts, builders, and communicators who can work across disciplines, define problems clearly, operate inside constraints, and stay grounded in mission purpose. Programs like NCAS invite students into authentic mission-style thinking before they are fully formed professionals. That matters because identity develops through practice. A student stops being someone who is merely interested in space and starts becoming someone who can contribute to a mission culture. NASA Jet Propulsion Laboratory, JPL. NASA is also trying to achieve something through science. Science is not simply the accumulation of facts. It is a method for reducing uncertainty about meaningful questions. Mars is one of the most meaningful places to apply that method because it speaks to life, climate, geology, habitability, and human destiny in space. And NASA is trying to achieve something through Mars itself. Mars forces better technology. It demands better autonomy, better systems integration, better sensing, better planning, and better operational discipline. In that sense, Mars is not just a destination, it is a proving ground. NASA science. So as you move through this project, keep one practical truth in mind. The teams that win are usually not the teams with the fanciest language or the most overloaded concept. They are the teams that combine boldness with discipline. They identify one mission clearly. They design on purpose. They explain trade-offs honestly. They understand constraints. They test early. They revise intelligently. They align as a team, and they make it easy for judges to believe that the mission deserves support. If you want a simple way to check the strength of your own proposal, ask these questions. Can we explain the problem in one sentence? Can we explain why NASA would care? Can we explain why our rover is designed the way it is? Can we show that we thought about risk, time, cost, and testing? Can every teammate describe their role? And does the whole document sound like one coherent mission case? If the answer is yes, you are getting close. If the answer is no, that is not failure. That is clarity, and clarity is what lets you improve. So take this seriously, but do not treat it like a stiff academic exercise. This is practical. This is applied. This is what it looks like when scientific thinking, entrepreneurial thinking, engineering discipline, and mission communication all meet in one project. You are practicing how to recognize an opportunity, build a team, define a mission, justify a design, manage uncertainty, and earn trust. Those are not just school skills. Those are professional skills. Those are mission skills. Those are leadership skills. Your work here begins with a proposal, but what you are really learning is how real exploration starts. It starts when a team looks at a difficult environment, understands that the need is real, and says, "We know what problem we want to solve. We know why it matters, and we are ready to make the case." In conclusion, this 7-week experience is an opportunity to practice how real missions begin. Through teamwork, discipline, creativity, and purposeful execution. You are not simply completing an assignment. You are learning how to identify a meaningful challenge, organize around a solution, and communicate why that solution deserves support. As you move forward, the next steps are clear. Get aligned with your team early, establish roles and expectations, decide on a focused mission pathway, and make sure every member understands the objective. Begin drafting your proposal immediately, starting with the executive summary, mission rationale, and early design concepts. Start working hands-on with the robotics kit as soon as possible so testing and iteration become part of your process, not something left until the end. Document what works, what fails, and what improves. Use each workshop to strengthen a different part of your project, ask questions often, and stay connected as a team between sessions. If you remain organized, proactive, and mission-focused, you will give yourselves the best chance to compete well, learn deeply, and create something you can be proud of when final presentations arrive. You got this. Have fun.